A few days ago, from when I'm making this video, there was a very intriguing conference in Switzerland. It was part of the International Space Science Institute, and during this conference, a lot of scientists presented a lot of exciting space-related work. But one of the studies really stood out, at least to me. It was a presentation about pretty much most of the recent exciting discoveries by the James Webb Space Telescope. And all of this was even published as a study that you can find in the description with the title The First Billion Years According to JWST. And in this paper, the researchers basically summarize all of the major and somewhat unexpected discoveries from the James Webb Space Telescope that are definitely going to be rewriting a lot of textbooks in the next few years. And so, hello wonderful person, this is Anton. Let's basically talk about this particular study, discussing some of its main points, but really discuss some of the biggest discoveries from the James Webb from the past 2 years. Because after these 2 years, it actually did change our understanding of pretty much everything in the entire universe, from stars to black holes to how galaxies form, and to even what happened in the first billion years after the Big Bang. And that's because James Webb was actually designed to answer a lot of questions about the distant universe, also referred to as the high redshift universe. And so even though the Hubble telescope could only actually see things up to about the redshift of 11, which represents the distance of the farthest galaxy it ever found, the one we've discussed in one of the videos in the description, GNZ11, the James Webb can see much farther, up to the redshift of 20, with one of the recent videos discussing the new record holder, the galaxy that you see right here at a redshift of 14.32. And I guess let's start with that, galaxies. So as you can probably imagine, James Webb found so many new discoveries about all sorts of galaxies out there. A variety of ancient galaxies that existed in the first billion years that turned out to be way more massive, way more luminous, and even way larger than we ever expected. Now, the important part here is that they're still not as big as the galaxies near us, they were still relatively small, but much larger than anyone ever expected, which basically implied that galaxies must have evolved very quickly from how we actually imagined it, or from how various simulations showed us over the years. And so, for example, going back to this galaxy, it's at least a few 100 million solar masses, so it's actually not that big, but it's extremely bright, it seems to possess a huge amount of star activity, and it's already out there 300 million years after the Big Bang, much sooner than anyone ever expected. It's also surprisingly long, like so many other ancient galaxies, seems to contain a huge amount of dust, and even surprisingly has oxygen. And it's actually the presence of oxygen and a lot of other elements that's even more shocking. A lot of these elements indicate that a lot of stars here already lived when supernova formed new stars, and then those stars possibly went supernova as well. And so in essence it implies several generations of stars have already existed here forming these complex elements. And I guess more importantly, this type of a galaxy has never been predicted by any theoretical models or any massive computer simulations that we've used before to try to estimate galactic sizes. For example, the most famous model, the Illustris project, with the model known as TNG50, does not predict anything like this at all, meaning that we have to rewrite a lot of textbooks when it comes to galactic formation and early galactic evolution. But that's obviously not the only thing that was discovered. On top of this, the scientists also discovered a lot of quiescent galaxies, or basically galaxies not even forming stars anymore, suggesting that they for some reason shut down their star activity really early, or quite the opposite, galaxies with a ridiculous amount of star formation, which also does not make a lot of sense. But this does indicate that a lot of these early galaxies seem to have a kind of an unpredictable, bursty star formation. That's literally the quote from the paper. They seem to have an unusual on and off mode, where sometimes they're on producing a lot of stars, and sometimes they're off doing nothing. Why? Nobody knows. Then, James Webb also discovered quite a lot of disk-shaped galaxies, and a lot of them very early, which basically implies that disks seem to form much earlier than ever imagined or ever simulated. And that was actually one of the stranger discoveries so far. Then they discovered a lot of red galaxies, or basically galaxies that are very dusty and don't have a lot of star formation. Once again, way more than expected, and something that's very difficult to explain. And you can actually learn about most of these discoveries in a lot of videos in the description. Then, just as surprisingly, it discovered early galaxies that already possessed a galactic bar, or even some kind of a bulge in the middle, implying that many of these shapes evolved super early. And that is something that's very difficult to explain. It was always believed that these shapes take much longer to form. And so here we have these shapes only a few billion years after the Big Bang. Which means that when it comes to galactic discoveries, there were just so many unusual mysteries. A lot of them still don't have a very good explanation, but it just means that something in the early universe was very different from what we imagined or from how it was modeled in different computer simulations. And so these discoveries about galaxies were definitely very odd. But that's just one of the mysteries. We also have the mysteries of stars. Because here there were a lot of observations when it came to a tremendous amount of star formation. Way more than expected, and even containing objects and things that nobody expected. For example, one of the major surprises was the discovery that approximately 10% of all of the stellar mass was inside various star clusters or cluster-like formations. So basically, these early galaxies were actually predominantly in these unusual cluster-like forms where all of the stars were basically chunked together, interacting and producing a lot of energy. And these were observed as early as 500 million years after the Big Bang. There's actually a really intriguing image in the study that shows us some of the examples, and here you can actually see that some of them are referred to as cosmic gems, firefly sparkles, or even things like cosmic grapes. A lot of these are basically clusters at very far away distances, whereas a few objects you see on top are individual galaxies. And in terms of size, they're not super big or super massive, so once again they don't actually violate the Big Bang theory, but they're still a lot more active and even a lot larger than anyone ever imagined. So for example, right here, the size is approximately 3,000 light years across. So that's about the size of a typical dwarf galaxy, or about 30 to 40 times smaller than the Milky Way. But because so much mass is observed inside these clusters, this actually provided one of the main answers that the James Webb Space Telescope was designed to solve. Turns out that these powerful emissions coming from a lot of these star clusters are very likely responsible for changing the universe completely. The process known as Reionization. These clusters were so ridiculously powerful and so extremely bright that they basically ionized all of the hydrogen gas in the universe in just a few 100 million years. And so these unusual objects are likely responsible for the ionization of the universe, but also enhancing the universe in elements like nitrogen, because many of them do show abundance of nitrogen in most of these observations, but most stars inside of them are extremely hot and very bright. Here we're talking about O-type and B-type stars. Although strangely enough, additional observations discovered that a lot of these stars and a lot of these clusters are also highly metallic, meaning that they contain stuff that's not hydrogen and not helium. And so even approximately 350 million years after the Big Bang, and here we're talking about some of these earliest galaxies discovered by the James Webb, researchers were already able to find nitrogen, carbon, oxygen, neon, argon, and sulfur. And in some cases, some of these stars were even at approximately 30% metallicity of the Sun, basically implying that the enrichment of these stars was super fast and everything evolved much faster than anyone ever imagined. Or basically the early universe was an extremely dynamic and very fast-paced place where things changed super quickly and most stars only lived for a few million years. And the entire universe self-enriched in a lot of elements extremely quickly as well. But as you can see from this graph, as you go back in time, less and less galaxies are visible to us, so once again, this does not violate the Big Bang theory. Some of these first galaxies and first stars are essentially where we kind of expect them to be. But here's the thing, still no actual first stars, or so-called population 3 stars. And that's actually one of the main missions for the James Webb, discovering first stars in the universe. And right now there have been some signs here and there, but nothing specific and nothing concrete. And so even after these 2 years, the population 3, or the first stars ever, still have not been discovered. But it did make a lot of discoveries about early black holes. As a matter of fact, it was even able to answer questions about black hole formation and quasar formation. Quasars are essentially extremely bright black holes in the middle of various galaxies that we can usually detect from extremely far away distances. And it's also basically a type of an active galactic nucleus. And according to the observations from the James Webb, they were already out there approximately 700 million years after the Big Bang. But James Webb discovered way more of them than anyone ever expected. As a matter of fact, 10 times more. So basically there were 10 times more black holes in the early universe than a lot of simulations or a lot of modeling predicted. Although here we're talking about supermassive black holes. Black holes that are millions or even billions of solar masses in mass. And one of the major questions that the James Webb Space Telescope allowed us to answer is how exactly these giants formed so early on. One of the biggest mysteries was actually discovering various galaxies and various black holes that were just way too massive for such an early universe. As a matter of fact, as you look back, you actually discover there are quite a lot of these massive black holes out there, but the size of the galaxy itself seems to grow smaller and smaller as you go back in time. And so a lot of these observations establish that apparently, as you go back in time, we even reach a time when the black holes were just as massive as the rest of the galaxy, or essentially all of the stars and all of the gas together were just as massive as the central black hole. And that's extremely different from the modern universe. In the modern universe, most central black holes are only about 0.1% of the entire galactic mass. Yet in the ancient universe, they were up to 50%. And that provided us with a very important proof of how they probably formed. Previously, there were two major solutions. Either black holes started very small, growing larger and larger by acquiring a lot of mass from the outside, which is usually referred to as the light seed model, or it was the opposite. The black hole started as huge chunks, possibly up to about 10,000 solar masses, and all of this grew much faster by combining with other massive objects. That model is referred to as the heavy seed model. And while the observations right now seem to suggest that all of these ancient black holes indeed started as the heavy seed, or basically early black holes possibly formed from a direct collapse of a lot of mass, very likely thousands of solar masses in mass in total, suddenly becoming these large objects in the middle of various galaxies. Although interestingly, this is one of the predictions from modern theories, and so here we don't actually have to rewrite textbooks just yet. But at least it answers one very important question, the formation of these early massive black holes. And then of course we have the question of reionization of the universe, which I briefly talked about previously, but here a lot of studies based on the James Webb observations were able to establish that black holes, or quasars, were most likely only responsible for about 25% of the entire reionization. And although some scientists previously assumed that maybe it was actually black holes responsible for everything, the observations from the James Webb suggest otherwise. And so during the reionization period, it's quite likely that the ultraviolet light from quasars was responsible for maybe about 25%, but the light from powerful stars in various globular clusters was probably responsible for the most. And since these objects represented at least 10% by mass of the entire galaxy and contained a lot of powerful stars inside of them, they essentially played the biggest role in changing the universe, making it transparent in the process. And they basically did this by forming these huge bubbles that expanded over time that eventually overlapped with one another, covering the entire universe. And that's of course because before this, the universe was mostly opaque to a lot of different types of light, especially the UV light, with the James Webb also confirming that at a redshift of about 5 to 6 or about a billion years after, reionization more or less finished. But here it was also able to show us the approximate time when it started, because we actually see the effects of reionization in a lot of these early galaxies already, and this is basically about 300 million years after the Big Bang. And though apart from the stars and the black holes, there were possibly some other sources for reionization, such as for example quiet galaxies or galaxies that were not as active, it definitely confirmed the main source. early massive clusters, or globular clusters, in a lot of different early galaxies. And that was actually one of the main discoveries last year. And so overall, a lot of super exciting and very unusual discoveries that in just 2 years completely changed our understanding of the entire early universe. Even though we assumed the early universe to be a certain way, it was definitely very different from what anyone imagined. But that's just after 2 years. We still have at least 18 more to go, and so we'll definitely be coming back and talking more about different discoveries in many videos in the future. On that note, well, that's pretty much all I wanted to mention, but I do recommend that you actually check out this particular study by yourself, because it's relatively easy to read, and it's actually a really good summary of pretty much everything, at least as of June of 2024. On that note, once there are some additional discoveries, we'll definitely come back and talk more about this in some of the future videos. Thank you for watching, subscribe, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, support this channel on Patreon by joining the channel membership or by buying the wonderful Bursty t-shirt that features James Webb on one of the designs. Stay wonderful, I'll see you tomorrow, and as always, bye bye.